Welcome to Introduction to Areas Between Curves by Conceptual Calculus. This video is part of a series on applications of the integral. In this video, we learn how to use a definite integral to find the exact area of a region between the graph of a given function and the horizontal axis. We start with a simple shape with an area that is easy to find, the rectangle. The area of a rectangle is height times width, so this rectangle has an area of 5 times 6, or 30 square units. Now consider the area between this curve, y equals f of x equals 1/4 x squared minus x plus 2, and the x-axis, from x equals 0 to x equals 6. Whenever possible, we always start with an estimate. The simplest estimate for the area of a region comes from putting the region in a box. The box has an area of 5 times 6, or 30 square units. So the shaded region with the curved top has an area of less than 30 square units. The shaded region appears to about halfway fill the box, so I expect the area of the shaded region to be about half of 30, which is 15. It is definitely less than 30. After we find the exact area, we will compare it to this estimate. The shaded region is more complicated than a rectangle because the height is not constant. It is shorter on the left and taller on the right. If only the height were constant, then the area would be very simple to find. The problem is more complicated because the height is varying, is changing. That is an indication that integration could be helpful here. We break the region up into several parts and approximate each part with a narrow rectangle. This solves the problem of the varying height. For each individual rectangle, the height is constant. We take the height of the rectangle from the curve. In this example, I am getting the height of each rectangle from the height of the curve on the right side of the rectangle. It is also possible to get the height from the left end, or the center, or some other point in the interval. You may have seen this in your textbook. You can see that the total area of all the narrow rectangles is close to the same as the area of the region, but not quite the same. The rectangles leave out some area that is in the shaded region, and the rectangles include some area that is not in the shaded region. Now look at what happens if we make the rectangles narrower and use more of them. As the rectangles become narrower, they follow the curve more closely. In the limit, as the width of each rectangle approaches 0, so that the number of rectangles approaches infinity, the rectangles follow the curve perfectly. In the limit, as the width of a rectangle approaches 0, the sum of the areas of all the rectangles is exactly equal to the area under the curve. To set up the integral, we start by understanding one rectangle very well. Then we can add them up. We need some way to keep track of which specific rectangle we are talking about. Instead of saying that we want the green one or the blue one, we use a variable as a unique identifier, sort of like the address of the rectangle. In this graph, the variable x gives the location of the right edge of the narrow rectangle. Because the variable x keeps track of which rectangle we are talking about, x is the variable of integration. Everything we do will have to be written in terms of x. In these problems, we always break a large thing up into small parts, and there is always some dimension that is very small, approaching 0 in the limit. In this case, that is the width of the rectangle. The width of the rectangle approaches 0 as we use a larger number of rectangles. As we move from the left side of a rectangle to the right side of the same rectangle, we go a little bit forward along the x-axis. If we are talking about a finite number of rectangles, each with a finite width, then we call this width delta x. That little triangle is a Greek letter delta. When we consider the limit as the width approaches 0, then we call the width dx. Now that we have notation for the way the region is broken up into rectangles, we need to remind ourselves of what we are trying to find. We want the area of the entire region, which we are going to find by adding up the areas of the narrow rectangles. So we need the area of one rectangle. The area of one rectangle is height times width. We have the width, it is dx. We need the height. The height is measured vertically, so it is y. Since we are integrating with respect to x, we write everything in the problem in terms of x. So we need to write y in terms of x. We use the function for the curve y equals f of x. That is 1/4 x squared minus x plus 2. Now we have all the parts we need to assemble our integral. The area of one narrow rectangle is height times width, so f of x times dx. To add the areas of the rectangles together, we integrate. Our variable of integration is x, so the limits of integration must be values of x. The leftmost narrow rectangle has x equals 0, and the rightmost one has x equals 6, so we integrate from 0 to 6. Now that we have set up the integral, we can evaluate it. We have the integral of f of x dx from x equals 0 to x equals 6. We put in the function f of x equals 1/4 x squared minus x plus 2 and use the power rule. The antiderivative of x squared is 1/3 x cubed. The antiderivative of x is x squared over 2. The antiderivative of 2 is 2x. Next, we substitute in the limits of integration. The upper limit is 6, so we substitute 6 in for x in the antiderivative. Then we subtract the same antiderivative with 0 substituted in for x because 0 is the lower limit of integration. 0 cubed or squared is still 0, so this part is very simple. Finally, we simplify the arithmetic and find that the integral is equal to 12. That means the area of the shaded region is 12 square units. Compare this to the estimate. We determined that the area was definitely less than 30 and appeared to be about 15. An area of 12 fits that description. When our calculation agrees with our estimate, we can have more confidence in our results. This was one of the simplest examples of finding the area of a plane region. In later videos, we examine regions that do not use the coordinate axes as boundaries, and regions that must be broken into subregions with a separate integral for each subregion. All of these problems will use the same basic method that was presented here. Thank you for watching Introduction to Areas Between Curves by Conceptual Calculus.